All right, so in this collection of videos, we're actually still going to be living in the world of these elliptic curve discrete log problems, but we're going to begin chatting a little bit about how hard this problem actually is, as well as a few different approaches to actually solve this problem. Naturally, we want to move beyond just a classic brute force approach, but we still want to be living in questions that are genuinely believed to be hard, because ultimately we're going to be building some crypto systems out of them. So what you're going to see down below is actually going to be a nice little sketch of what's referred to as a collision algorithm or a meet-in-the-middle attack. So the idea here is actually very similar to the collision algorithms that we looked at for the classic discrete log problem. Naturally, we have to make a few slight modifications to reframe this in the world of elliptic curves, but the general idea is going to be pretty similar. So what's going to happen here is that we're going to be playing the role of Eve, so I'm that evildoer in the middle, and my goal is to identify this special little number n that's going to make this equation true. So the idea is that Alice has released to the world this point P and this point Q, and there's a special little bond between those two things that says that if you take P and add it to itself n times, it's actually going to return this point Q. So Eve's goal is then going to be to try to identify what that tiny little n value happens to be. So naturally, we could do this classic brute force where you just take P and you add it to itself a whole bunch until you actually magically land at Q. But if P and Q are coming from some massive elliptic curve over some huge finite field, and that n value is up in the trillions or billions or even bigger than that, that's going to take a really, really long time. So what we need to do is we need to be a little bit more clever. So what we're going to do here is we're going to invoke a collision algorithm. So the way that these algorithms work is that we're going to form two little lists, and the length of these things we're going to chat about a little bit more in a bit, and we're going to run these things until there's some form of intersection between them. So list 1 is going to be some random multipliers of this point P. So you're going to take R of them, and I'm going to denote them by J1 up through JR. If you want those just to be 1, 2, 3, 4, 5, all the way up to R, you could do that. But for now, we're going to let them just be whatever they want to be. And then we're also going to take a collection of other points, which we're going to denote K. So the same type of thing. We're going to randomly choose some numbers between 1 and P. In particular, we're going to choose R of them. So what ends up happening is that we're going to form two lists that are each going to contain R elements. So I'm going to get J1P, J2P, all the way up to JRP. So just nice little multipliers of P. And then list 2 is actually where we're going to slip in this Q. So I'm going to take this K1P, so that extra random little K. So multiply that by P, so K1P, and then I'm going to add on a Q. And I'm going to do that for every single element in that list too. So they're fairly easy to construct, these things. This is where we naturally have to have an efficient way to actually compute what some multiple of P is going to look like. Luckily, we have that. This double and add algorithm is very fast. It gets a little bit worse when I have to do it a whole bunch of times, but it's still genuinely a decent approach. So now I have these two little lists, and what I'm hoping to see is that I want to have a collision between these two lists. I'm not necessarily guaranteed a collision if I have a small list 1 and a small list 2, so we're going to have to talk about how big these lists actually have to be. So for right now, we're just going to assume that they've been made large enough so that I'm going to have some intersection between the two. So what's going to happen is that some J sub U, so one of these things up here, is then going to match with one of these things down there. So you get an intersection. So I don't necessarily know which one it's going to be, but I know that there's going to be some little multiplier of P that's going to equal some multiple of P plus a Q. Well, you can see that at this point, you can actually solve for Q. So you move this little point, KVP, over to the left-hand side, and then you factor out the P, and you're going to see this nice little expression emerge. So now you can see that this Q point is going to be achieved by taking J sub U minus K sub V, whatever that integer happens to be. You're going to take that many copies of P to actually emerge as this point Q. So what ends up happening is that this little thing right here is actually going to be your n value. It may end up firing off a negative number, so you're going to have to do some reducing afterwards. It may not be the most efficient version of that thing, but it will give us an option to actually solve this thing. So then you have to lean a little bit upon, where are these numbers actually coming from, kind of go back to the original definition of what these discrete log problems are all about, and then you're going to return that thing back to the user. So what we want to dwell on a little bit is how long these lists actually have to be. So I want to somehow ensure that I have enough stuff, but not too much, because I don't want these lists to be truly massive. I want to go along until I can safely assume that I'm actually going to have a match. So what ends up happening is that if you take this little prime that's going to be making up this finite field, so that's assumed to be pretty big. If your r is decently, larger than that square root of p, what's going to happen is that r is going to be something like 3 square roots of p. So pretty big list that we're going to be forming. Then we have a pretty good chance, and by pretty good I mean about a 99.9% chance, that there's actually going to be some type of collision. So at the rest of this section, we're going to be chatting a little bit more about what this idea of very good chance and how this random little multiplier of 3 times the square root of p is actually going to come about. So we have kind of the rough framework for how this collision algorithm is going to work. It's not so terrible to implement. I'm actually going to ask you guys to create your own version of this collision algorithm. So you create a couple lists, find an intersection, return this little value n back to the user, and everything is great. The kicker here, though, is what is this stopping point? And as we just mentioned, the stopping point is going to be about 3 square roots of p, and the reason for that still needs to be fleshed out. So that's actually what we're going to be doing in the next couple of videos, is doing a little bit of background theory to talk about where that particular bound is actually coming from.